All right, welcome back. We continue in chapter 5. Section 5.5 is on indexed families of sets. Okay, and the point of this section is just to expand our definition a little bit for unions and intersections. So the point is we have already defined, given two sets, A intersect B and A union B. Okay, so what if we have three sets? Well, you could take like A union B union C. This is okay, right? Because here I'm taking the union of two sets. This gives me a new set. And so now I take the union of this set, and this gives me this set. Of course, you could ask, well, what if I took A union B union C? But one of the theorems that we didn't prove last time, but you're supposed to prove as practice, is that union is associative, so these are the same thing. Which means that you could talk about the union of three sets. All right, in the same way you could talk about the union of four sets or five sets, right? So since set theory union is associative, you can now take, right? Now I'm running out of letters, so I can take like this. And what we've defined, like using this definition, we could basically define unions of any finite number of sets. What's not included in this definition is if I want to take a union of infinitely many sets. But it turns out that this definition also makes sense. You can take unions and intersections of arbitrary numbers, including infinite numbers of sets. And in fact, many times it's very natural to do so. But since it's not covered in our definition, we need to write down a definition that will cover it. Okay, so here's the definition. Let's let script C be some family of sets. This is potentially infinite. And I'll give you some examples in a second. What I'm going to define is the union over C is the set of all elements that are in at least one of the sets in C. Okay, so C is a bunch of sets, right? Like A1, A2, A3, A4, A5, for example. That could be one example. We write the union the following way. So we're using a big union sign. And so if I write this, what I mean is take the union of all sets X, where I'm taking X to be in the family of sets C. Okay, so here it's like I'm using a delimiter to say what my union is over. In exactly the same way as when you take an integral, right? You use delimiter to say exactly what your integral is over, or if you take a sum, you use delimiter to say exactly what your sum is over. Here I'm using a delimiter to say I'm going to take the union over all sets X in C, and X is like a dummy variable here. And what this means is this union is the set of all elements X such that X is in X for some X in C. Right? This set is exactly what I defined above. It's a set of all elements that are in at least one of the sets in C. Okay, and just if you're following along at home with LaTeX, to get this kind of union, you should use \big cup. So this is bigger than the normal union thing, and it also will allow you to take delimiters. So to get exactly where we're here, then you'll do an underscore, and then you'll say X in, and then maybe math cal C. This is how you get whatever in here. Okay, similarly, the intersection over C is defined to be the set of all elements that are in every set in C. That is, so this you do with a big cap. You take the intersection over all the sets X and C, and this is defined to be the set of all X. such that X is an X for every X in C. Okay, and the point is that these definitions are just the ones that will make sense. Right? You take any number of sets you want. If you take their union, what that means is just throw everything that's in any one of the sets into this huge set that's the union. Again, you take any family of sets, finite or infinite. What should their intersection be? It should be the elements that are in every single one of the sets, right? That'll sort of appear in the overlap. So now this is defined. Okay, now frequently, I don't know, I have a blank page here. Frequently in like real applications, there is some index set, lambda, where you have one set, A alpha, for each alpha in lambda. So for example, let me give you a concrete example. For example, we might have sets like A1, A2, A3, A4, A5, right? An infinite number of sets. If I want to take their union or their intersection, like this whole set of sets might be the family C, right? I have infinitely many of them. But these sets are indexed by the natural numbers. So here, these are indexed by n. So in this case, the family of sets C, that's just all the sets, but they're indexed by an index set, the natural numbers, where you have one set for each natural number, right? We have one set, AI, for each I in n. And if you have some sort of index set, it's like the index is keeping track of your sets for you, right? The family C, that's just all the sets, but you can keep track of them with some index set. And then if you have such a set, an index set, then when you write the union or you write the intersection, you can write it over the index set instead of over C, right? So in this example, you could write what we just defined was the collection of all X in C, X, this is the intersection of all the sets. Here you're writing the intersection just in terms of what sets you're intersecting, essentially. But another natural way to write this is the intersection over all natural numbers I of AI. Right, so here now, instead of writing the intersection over the family of sets, I'm writing the intersection over the index set. I'm saying, okay, well, take each natural number and intersect AI, the set indexed by that natural number. And another way to write this is the intersection from I equals 1 to infinity of AI. All of these are valid notations for the intersection of these sets in all these sets in C. Okay, so these are all just all the elements that are in every one of the AIs. Okay, and it's very natural. Things like this are very natural in mathematics. They'll appear all the time where you want to take some kind of union or intersection over some large family of sets. Okay, so let me give you some fairly natural examples. Here's the first example. So for each natural number n, let's define the set I sub n, which I'll take to be the half open interval from 0 to n. Right? Now I could let C maybe be the family of sets A1, just I1, I2, I3, I4. Okay, then quick brief quiz. Okay, by the way, here by natural numbers, for today, let's just start them at 1. Otherwise, I think I0 is not actually defined. So just on your own, I want you to just tell me what are these, what is this, was the intersection And what is the union? Okay, hopefully you've realized that what these sets look like, right, is right, like here's 0, there's 1, 2, 3, 4, and like I1 is this set, right? I2, I'll just draw them above, it's like this set, I3 is this set, and I4 is this set. So if you take the intersection, you just get back this I1, and if you take the union, you just get back I4. It's because these sets are sort of nested inside one another. Right, but another way to write this is that this is the union from I equals 1 to 4 of II. Again, just for practice with notation. Right here, you could think of there being an index set where the index set is just a set consisting of 4 elements. Here, the index set is lambda equals 1, 2, 3, 4. Again, the index set just indexes the sets. Of course, we could allow other index sets. So maybe I should ask you, what is, if I take the following, I equals, let's say, take the union of all I and n of II. So what happens if you take the union over all the natural numbers? Well, hopefully it's not so hard to see that, okay, let me just, for notational purposes, write this as the union from I equals 1 to infinity of II. Hopefully it's not hard to see that what you get is you get every non-negative real number, right? Because every non-negative real number is eventually in one of these INs. Okay, and I guess maybe I'll give you another example. Let's take some example where we're indexed by something maybe kind of crazy. So let's take in R2, let's let C be the collection of all unit disks with any center. So, right, what's the picture? The picture is we have R2, and by unit disk, I mean a disk with radius 1. That should be what unit disk means, right? So you of course have what you think of as the unit disk. That doesn't look very circular, but it is. But also, like, you have one of these, right? There's for every center you pick, there's a unit disk there. So then, like, I could take some index set. Let's say I take, okay, so let's actually give these things a name. So let's say that the disk with center, if you're centered at A comma B, let's call this thing B of AB. As in the ball centered at the point AB. Now I could do something like take the union over all A and R of BA0. This is now a union of infinitely many sets. In fact, indexed by their real numbers. So tons and tons of sets. And then I could ask you, what does this look like? That's I think an interesting question. So what does this look like? Well, what I'm taking is I'm taking the union of all of the unit disks. By the way, by unit disk, I mean these things are all filled in. So I'm counting all the points in the interior. here I'm taking the union where the center of my disk has a y coordinate of 0. So this union, what does it look like? Here 0, 0, that's one of my disks. Also like 0.50, that's one of my disks. Like 1, 0, that's one of my disks. This union takes into account all of these disks. And if you take the union over every possible disk here, what you get is you get this rectangular strip. You get this entire rectangular strip. So this is a rectangular strip going off infinitely in both directions. So between -1 and 1 on the y-axis, say. There's, of course, a more precise way to write down the set, but just want you to think about it like this. Okay, so here's an example where like you can now cover the entire real two-dimensional plane by these unit disks. You could take the union over all of them, for example, or you could take some union over some nice index set of them. Okay, and stuff like this, like if you take real analysis, you'll write notation like this all the time. It's important to get comfortable with notation. Okay, and now that we've defined this, you should ask what properties like this kind of union and this kind of intersection have. And the point is that they basically have all of the properties that you expect. This is sort of a mild generalization. And the proofs are not that different from the case of just taking two sets. In other words, if you're trying to prove that something is in a union, you just need to show that that element is in at least one of the sets, right? So before when you want to show that something was in A union B, you show it's in A or you show it's in B. Now, if you want to show that something is in the union of all of the BA zeros, you should show that it's in one of the BA zeros. Same thing with the intersection. So that something is an intersection, you need to show that it's in every single one of the sets. So the properties that you expect are true for these things, and I'll leave the proofs as an exercise. Of course, I should give you at least one proof. So let's prove one of the things in this theorem. Okay, so let's let let lambda be a non-empty index set. Could be infinite, could be finite. And let's let A alpha be an index family of sets. Okay, so I have a bunch of sets indexed by the lambda. I have one set for every element of lambda. Then the following things are true. So 1, for each beta in lambda, let me write down the two sets I want to talk about, and then you can think about what I should put there. 2, for each beta in lambda, I could take the union. And 3, I'll call De Morgan's law. Remember, De Morgan's law was about taking complements of intersections and complements of unions. So let's leave some space here. Sorry. Okay, so now I want you to figure out what this theorem should say. So if you look at the intersection of a bunch of sets and you pick out any one of the sets, that's what's happening here. Hopefully, it's reasonable to you that the intersection should be contained in any particular one of the sets. What this is saying is that the intersection is contained in any one of the sets. Similarly, hopefully it's not so hard to see that any one of the sets is a subset of the union. What about De Morgan's laws? De Morgan's laws said that if you take the complement of an intersection, it should be like the union of the complements. Right? If you take the knot of an and, it's like an or of the knots. So this should be the union over all alpha and lambda of A alpha complement. And the union of the complement of the union is the same thing as the intersection of the complements. what this theorem is saying is just that this more general definition of intersection and union over any index set just behaves the way that you expect. Okay, so let's prove this. Let's just prove this one. Because what you'll see is that the proof is not so different. This is not really a new proof technique. It's just applied to a slightly more general definition of intersection. Okay, so let's prove the first of De Morgan's laws. Let's prove both inclusions. Okay, so I'll prove the left-hand side is included in the right-hand side. Again, there's nothing new here. How do you prove equality? You prove both inclusions. How do I prove this inclusion? I'll do an element chase. So let's suppose that X is in the left-hand side. Oops, the intersection over all alpha and lambda of A alpha complement. What does this mean? This means that X is not in the intersection. If it's in the complement of the intersection, it means it's not in the intersection. Since X is not in the intersection, what was the definition of the intersection of these sets? The definition of the intersection of these sets was all the elements that are in every single one of the A alphas. So if it's not in the intersection, it means there is some beta such that X is not in A beta. By the definition of the intersection, this means that there exists some beta such that X is not in A beta. But what does that mean? So I'm trying to prove that X is in this right-hand side right now. So I need to prove that it's in one of the complements, but X right now is not in A beta. So X is in A beta complement. And now since it's in A beta complement, it's certainly in the union of all of the complements by the definition of the union. X is in the union over all of these alphas, A alpha. Okay, so it's an element chase using the definition of the intersection, the definition of the union, which is exactly how you prove the original De Morgan's law for two sets. For the reverse inclusion, let's suppose that X is in the right-hand side. So X is in the union of the complements. Right, by definition of the union, this means that there exists some beta such that X is actually in A beta complement. If it's in the union, it means it's in one of them, at least. Hence, X is not in A beta, because that's the definition of the complement. Since X is not in A beta, it means it can't be in the entire intersection, because the entire intersection consists of those elements that are in every single one of them. X is not in this single one of them. So by the definition of the intersection, X is not in the intersection over every alpha. And by the definition of the complement, X is in the complement of this set. And so I've proven both inclusions, so this finishes the proof. Because if you go back and look at the proof of De Morgan's law, in the two-set case, it was basically exactly the same thing. Okay, and the moral of the story here is just that intersections and unions behave just as you expect, even if you take the intersection or the union of infinitely many sets. Okay, so that's all I want to say about section 5.5, and I've still got some time, which means that I want to move on to chapter 6. And chapter 6 is on one of the most fundamental concepts in mathematics, and that's the concept of a function. Okay, so if we were in person, I would ask you, what is a function? And one thing that I think is true, and in fact, I used to joke with my office mates in grad school about, is that even most math majors who are graduating from UCSD do not know the definition of a function. If you ask them what a function is, I think a reasonable number of them would be like, oh, it's like f of x equals x squared, which is an example kind of a function. It's actually, I don't know what function that is actually if you just tell me f of x equals x squared. So what is the definition of a function? Well, since this is University of Washington, and I went to grad school at UCSD, and UW is a much, much better school than UCSD, of course. I expect that all of you, when you graduate, when I come up to you and I ask you what's the definition of a function, you will know exactly what a function is. What is a function? Here's the definition. Let A and B be sets. We need to start with some sets. A function, f from A to B, is a rule that associates to each A in A exactly one element, f of A in B. This set A is called the domain of f. And the set B is called the codomain of f. Okay, so what is a function? A function is a domain, a codomain, and a rule. A rule that needs to take each element of the domain and assign it one element of the codomain. That's what a function is. It's a domain, a codomain, and a rule that assigns to each element of the domain exactly one element of the codomain. And this, whatever the element you assign it is, that's just what we call f of A. This is the element that you're assigning to A by this function f. Okay, so some notes are in order. So first of all, LaTeX, to get this arrow, the quickest way to do it is to do \2. You could also do \right arrow. And if you wanted a long right arrow, you could do \long right arrow. There's sometimes when you want to like label an arrow, and so you can do that. Secondly, some notation, right? This notation, what does this mean? This means that the name of your function is f. This colon is just saying my function's name is f, and I'm about to tell you the domain and the codomain of the function. This is the domain. This is the codomain. So this is how you notate a function with the name f with domain A and codomain B. And when you see this, you read this as it depends on the context. So you might be read it as f a function from A to B, or f is a function from A to B. So like in the definition, when I wrote it here, if you read this sentence in English, you would say a function f from A to B. Okay, but if you're in the middle of a proof and you say like let f from A to B, you should really read this as let f be a function from A to B, right? Or if I say suppose f from A to B is a function, you would say suppose f from A to D is a function. That's how you read this. This is read something like f from A to B, or f a function from A to B. Okay, and then the last note here is this word codomain. So maybe some of you in high school or something called this the range. But range we should actually reserve for something different, namely the set of actual outputs of the function. So I'll define that in 1 second. The point is that, I mean, actually, hopefully you remember this from linear algebra. To be honest, I took this section of the notes directly from my Math 308 notes. So I know you covered this in Math 308. The codomain of a function is just all the places, all the natural outputs, where all of your natural outputs live. So the word co in mathematics, I'm like going kind of far afield here, but somehow the word co in mathematics means flip all the arrows, like in category theory. So like, right, the domain is on this side of the arrow and the codomain is on this side of the arrow. So if you flip the arrow, then like this would be the domain of your function, right? Roughly speaking. There's things like kernels and co-kernels. There's dimension and codimension. Somehow the word co means flip the arrow, which means that there's actually like a joke in mathematics. So if you flip an arrow twice, you of course get the same arrow back. So if you take like the codomain, this should just be the domain. So a nice category theoretic joke that probably none of you will understand because I haven't really explained this is every nut is a coconut, right? Because a co-nut is presumably a nut where you flipped all the arrows. So a co-nut is just a nut. Okay, but I'm kind of being a nut here. So let me move on to the next definition in black ink. So let f be a function from a to b. Whoops. If a is an element of a, then this element f of a, which is an element of b, is called the image of a under f. Right? So if f is understood, you might just say the image of a. But if you want to specify f, you say the image of a under f. Okay, similarly, if x is a subset of a, then we define, I'm going to now define a new symbol, f of x. Right, so what's the difference between these two things? Here, a was an element of big A. And the function took little a as input and spit out f of a as an output in B. So the function told you exactly what f of a is. Right now, if x is a subset, that means it's a whole bunch of elements. I haven't defined what this notation means yet. I've only told you what f of an element means. But what this notation means is the set of all f of a such that a is an x. In other words, you take every element of x, you apply f, and you collect all those objects together. This is a new, so this is a set. This is a subset of B. But this is called the image of x under f. Okay, so you use the word image to mean what the function maps your set to, or what the function maps your element to. Right, so the picture here is if you have a function from a to b, like this, you have some elements here, and they map to some elements here. Maybe these two map to the same element. Right, so if like this element here, if this element is a, then this element is f of a. And if this subset is x, maybe I should have done that in a different color, then this subset over here is f of x. Okay, now if you consider all of a, then you take this set f of a, the image of the entire set A, that is to say all f of a over every a in A. This is called the range of f, or sometimes just the image of f, the image of your entire function. Okay, and this is the definition of range. The definition of range is all the things that actually occur as outputs. all the things that actually occur as outputs. The codomain could be bigger. The codomain is just a space where all of the outputs naturally live. So let me give you an example, a really concrete example. So everybody's favorite function, let's consider the function f from R to R that maps f of x equals x squared. It maps every x to its square. Okay. By the way, when I said earlier that a bunch of people might say, oh, a function is like f of x equals x squared, that's f of x equals x squared does not define a function. Because in order to have a function, you need to know a domain, a codomain, and a rule. So if I say x squared, that's basically telling you the rule. It's not a function until you know what the domain and the codomain are. So here I've actually defined a proper function. I said the domain is real numbers, the codomain is real numbers, and the rule, you take every real number and you just square it, and that's your output. Okay, so here the domain is the reals and the codomain is the reals. That's natural, right? Because anytime you square a number, you get a real number. So squaring, I mean, because the reals are closed under multiplication, they're closed under squaring. But here, what's the range of f? The range of f is just all of the non-negative reals. So this is not the same thing as the codomain in this case. So many times when I do this example in linear algebra or in Math 300, people say, well, then why don't you just define the function to have codomain that's equal to its range? Which is a really natural question to ask. The point is that when you're defining a function, there's often a very natural domain and a very natural codomain. So what do I mean by this? Like in calculus, you studied functions from the reals to the reals, which meant that, for example, you could compose functions, right? So if g was a function from the reals to the reals that added 1, it made sense to talk about g of f. And it made sense to talk about f of g. Because f and g were both functions from the reals to the reals. So if you took f, after you did that, since you're in the real numbers again, you could then apply g. If I defined f to be from the reals to just the non-negative reals, then technically I cannot apply g to this because it has the wrong domain. Of course, this is a subset of the domain of g, but nevertheless, it has the wrong domain. So in calculus, when you want to compose functions or you want to add functions, right? F plus g is a new function from R to R. The fact that all the domains and all the codomains matched meant that you could compose them, you could add them, you can multiply them, and then all the functions had the same domain and codomain. Which is why the natural codomain of the function f is still the real numbers, not just the non-negative real numbers. The appropriate way to think about this is the codomain is R. It's just that the range or the image of f is just the non-negative real numbers. Right? So really, if I wanted to talk about, I mean, you could define a new function. You could define h from R to 0 infinity, defined by h of x equals x squared. The point is that these two functions are different functions. Now, they have the same rule for every element of the domain, but since they have different codomains, you should regard them as different functions. A function is a domain, a codomain, and a rule. Okay, similarly, I could define a different function. Yet again, let's call it L from the integers to the integers, defined by L of x equals x squared. What does this function do? It takes every integer and it squares it. These are all different functions. They have like the same sort of rule, but because they have different domains and codomains, they are different. And you even sort of think about these functions differently. You do different things with these functions. For example, it's f is like a continuous function. L, okay, it turns out that that's also a continuous function depending on the topology you put on Z. That's, I'm again going far afield here, but L has different properties because it isn't defined in between the inputs somehow. Okay. Now, the bad thing about thinking of functions like f of x equals x squared is that you might be led astray into thinking that every function is defined by some algebraic rule. Right? Like here, there's a very clean way to write down what the function does. If I just say you just square it, but not every function can be written like this, right? So there are all kinds of crazy functions out there. So one totally legitimate way to define a function is just to specify explicitly what it does to every element. So let's let A be the set A1, A2, A3, A4. Let's let B be the set B1, B2, B3. And let's define a function f from A to B by, let's say, f of A1 equals B2, f of A2 equals B1, f of A3 equals B2, and f of A4 also equals B2. This is a totally legitimate way to define a function. Why? A function is a domain, a codomain, and a rule that assigns to every element of the domain exactly one element of the codomain. So here I've told you what my domain is. I've told you what my codomain is. And for every single element of my domain, I gave it exactly one element of the codomain. Right? It was okay that some of them map to the same element, as long as each of them only maps to a single thing. Okay, and if you have some small baby function like this, you can actually draw explicitly what it is using what I'll call an arrow diagram, which I sort of already used earlier. Right, since this is like a very finite kind of function, I can just write exactly what I mean by it. Right, so I can draw A1, A2, A3, and A4. I can draw B1, B2, and B3. And this function, I can draw the rule by just drawing an arrow from the input to the output, right? So f of A1 is B2, f of A2 is B1, f of A3 is B2, f of A4 is B2. And this is a totally legitimate function, and I've drawn a picture of it. Okay, here, what's the range of f? The range of f is just the set B1 comma B2. So it's not all of B, it's a strict subset of B. Okay, now from this picture, what is it about this picture that makes this picture a function? The thing that makes this picture a function is that every arrow here, sorry, every element here has one and exactly one arrow coming out of it. So exactly one arrow out. It needs to have an arrow out because the function needs to be defined on that element. And it needs to, the function needs to associate only one element of the codomain, which means I can only have one arrow coming out of each of these dots here. On the right-hand side of this picture, not every element needs to have an arrow going into it, right? B3 doesn't. And you don't need to have only one. For example, B2 has 3 arrows going into it. So the number of arrows in here doesn't matter. I mean, in order for f to be a function. Okay, and in my last 2 minutes, let me just make one last definition. So let's let f from A to B be a function. And suppose that little b is an element of the codomain. Now, if there exists some a and a such that f of a equals b, in other words, if the function actually maps something to b, we call a pre-image of b. So a pre-image is something that maps over to it. Okay, so note that an element of B may have none or many preimages. A preimage is just something that maps over to it. There could be nothing, there could be more than one. There could be one. Similarly, for a subset Y of B, the set of all preimages of elements of Y is denoted by the following notation: F inverse Y. This is a set of all A and A such that F of A ends up in Y. This is all of the elements in A that map to something in Y. And this is called the preimage of Y. Okay, note that here mathematics has an overloaded notation because this notation does not mean that F is invertible. That does not mean F inverse. Right, so this is sort of an overloaded notation. But the point is that I'm putting a set. So I didn't say F inverse of B. If I wrote this down, then it would be really confusing because then I might mean the function F inverse. So I really have to say a preimage of B. But since I'm talking about a whole set, I guess if F is invertible, this is still sort of ambiguous, but this is unfortunately the common notation for the preimage of a set. It's F inverse, essentially, is how you like this notation looks like. But that's the set of all pre-images of elements of Y, which is called the preimage of Y. So if we go back to this example, let's just list some features of this function. The image of F, that's the same thing as the range. That's B1, B2. I could say A4 here is a preimage of B2. Or I could say the preimage of the set containing B2 is, this is defined to be all the elements that map over into the set, which is A1, A2, A3. Sorry, A1, A3, A4. That's what it is, right? Okay, so A4 is a preimage of B2, but the preimage of the set containing B2 is the set A1, A2, A3. Okay, so I'm definitely out of time here. We will continue talking about functions for the next couple of lectures.